Our next task is going to be understanding the trigonometric functions as functions of real numbers rather than angles, as functions of the measure of the angle rather than of the angle itself. Now, we are often a little bit sloppy here, and the reason is because no matter which way we think about the trigonometric functions, as functions of an angle or as functions of a number, being the measure of that angle, we get the same answer out of it. So we can move back and forth between these two ways of thinking about them fairly easily without trouble. Now, the way that we're going to define trigonometric functions of a real number, though, is by taking things back to an angle in standard position. But now we're going to connect things up with a special circle. The unit circle is what we're going to be looking at, and it's the circle with radius 1, hence unit, centered at the origin. In other words, it's the solution set to the equation x squared plus y squared equals 1. And we've sketched out the unit circle here. So on the x and y axis, the unit circle is the one with a radius of 1. So in particular, the points that we can write down immediately that lie on the circle are the ones that lie on the axes. So the rightmost point of the circle is at the point 0, 1, top at 1, the top at 0, 1, the rightmost at 1, 0, the leftmost at -1, 0, and the bottom at 0, -1. And we've got this circle here. And now what we can do is we can look at what we get if we want to take sine of some angle theta here. Well, as we saw last time, we can do this in the following way. We can look at the terminal side of such an angle. So maybe theta looks like this. And what we did last time is we defined the sine or cosine of an angle based on points that lie on this blue line in terms of the x-coordinate, y-coordinate of that point and the distance from that point to the origin. Well, whenever we draw out the terminal side like this, this side is definitely going to intersect the unit circle at some point. So it's going to intersect the unit circle at some point x, y, corresponding to theta. And so we can describe this point as the point corresponding to theta. So the point corresponding to theta on the unit circle is the point where the terminal side of an angle with measure theta intersects the unit circle. And the thing that works out really well for us when we go to compute sine, for instance, of this angle is that we know that sine of this angle theta will be y, the y-coordinate of this point, divided by r, where r is the distance from the origin to the point x, y. But we know that the point x, y lies on the unit circle. The unit circle consists of all points that are a distance of 1 away from the origin, and so that means that the denominator of this fraction is just 1, which means in particular that it can go away. So the point is that if we sketch out an angle theta, and we draw its terminal edge, and we look at the point where that edge intersects the unit circle specifically, then the y-coordinate of that point will be exactly sine of theta. Similarly, the x-coordinate of that point will be exactly cosine of theta. We could even have defined the trigonometric functions in this way, using the point where the terminal edge of theta intersected with the unit circle. So the point here, the point corresponding to theta on the unit circle, is the point where the terminal side of the angle with measure 0 intersects the unit circle. The x-coordinate of this point is cosine theta. The y-coordinate of this point is sine theta. And we can compute tangent by remembering that tangent is sine over cosine. And once we have the sine and cosine of an angle, we can figure out all of the other four trigonometric functions very easily. So this is how we can interpret another way that we can interpret sine or cosine of an angle. Now, one thing that thinking about the trigonometric functions in terms of the unit circle does for us that's very helpful is that it lets us calculate angles that lie either vertical or horizontal. So we can ask something like, what is sine of 90 degrees? What is cosine of 3 pi over 2? What is tangent of pi? And I also want to look at what is tangent of pi over 2. We can do a few of these. So let's look at that using the unit circle. So we've got x, we've got y, and here we go. If we want sine of 90 degrees, what we can do is we can look for a 90-degree angle. Now we know that a 90-degree angle is exactly 1/4 of the way around the circle. So we go to a direction of 90 degrees, we take the terminal side up like this, and we see where does that line meet the unit circle. We see that it meets the unit circle at the point 0, 1. Therefore, sine of 90 degrees, which is the y value of the point where the blue line intersects the unit circle, is 1. So sine of 90 degrees is 1. Similarly, we can look at cosine of 3 pi over 2. Now remember, pi over 2 radians is 1/4 of the way around the circle. Pi over 2 radians is the same as 90 degrees. So 3 pi over 2 goes pi over 2, 2 pi over 2, 3 pi over 2. Here's 3 pi over 2 radians. And so the angle 3 pi over 2 radians goes straight down. Now that point where the curve intersects with the unit circle is the very bottom of the circle, which is at 0, -1. So cosine of 3 pi over 2 is going to be the x-coordinate of the red point, where the red line intersects the unit circle. The x-coordinate of that point is 0. Now, if we want tangent of pi, the easiest way to do that is to work it out as sine of pi over cosine of pi. So let's do that. Let's take an angle of pi radians. That's going to go around like this. Pi radians is halfway around the circle. We can draw our green line and see where it intersects with the unit circle, and we can see that it intersects the unit circle at the point -1, 0. So tangent of pi is sine of pi over cosine of pi. Sine of pi is the y coordinate of this green point, which is 0, and cosine of pi is the x coordinate of that point, which is -1. 0 over -1 is 0, and so we have that tangent of pi is equal to 0. Finally, let's look at tangent of pi over 2. Well, this is going to be the same as sine of pi over 2 over cosine of pi over 2. We actually worked out sine of pi over 2 already. We just wrote it as sine of 90 degrees, but that's the same thing. Sine of pi over 2 is 1. Cosine of pi over 2 is going to be the x coordinate of the point where the blue line, corresponding to pi over 2, intersects with the unit circle. And so cosine of pi over 2 is 0. So what we find is that tangent of pi over 2 is actually undefined. It turns out that sine and cosine are defined for all real numbers that you could put them in, because you can always find the x-coordinate and the y-coordinate of the point on the unit circle where the terminal edge of the angle intersects it. However, the other 4 trigonometric functions all involve ratios that have something in the denominator. And if that thing in the denominator, like the cosine right here, happens to be 0, that means that function is going to be undefined. So some of our trigonometric functions are going to be undefined at some points. We're going to look at that again in a few moments. One thing that we can do is we can use this interpretation of sine and cosine of an angle to understand more easily what happens when we start transforming functions. So let's look at some of these. So we have, let's suppose that we have some angle here, some angle theta, and let's say that this point that it passes through on the unit circle has coordinates 4/5, 3/5. That is in fact a point on the unit circle, so it's a point that we could possibly go through. So we have that, for instance, sine of theta is equal to 3/5, because that's the y coordinate of that point. Cosine of theta is equal to 4/5, because that's the x coordinate of that point. And now we can ask things like, well, what's cosine of theta plus pi? Now, what this does can be interpreted in terms of the graph, in terms of the unit circle. If I look at an angle of theta plus pi, that involves an angle moving an angle of theta like we have, and then moving an angle of pi, which is exactly halfway around the circle. What that means is that the angle theta plus pi is going to be exactly opposite the angle theta. So in this diagram, the yellow angle here is theta plus pi. We move theta and we've moved another pi. Now what we can do is use the symmetry of the plane to note that the green point here, which will define cosine and sine of theta plus pi, is exactly opposite the blue point, which defines sine and cosine of theta. And so in particular, it's going to be exactly opposite, which means its coordinates are just going to be the negatives of the coordinates of the blue point in quadrant 1. So this means that cosine of theta plus pi is going to be the opposite of cosine of theta, which gives us negative 4/5. Similarly, sine of theta plus pi is going to be negative sine theta, which in this case means negative 3/5. So what we see from this is that adding theta to pi inside the trig functions change the cosine and the sine of that angle to their negatives. They keep the same absolute value, but they change sign. So similarly, if we move pi in the negative direction, we're going to get the same sort of thing. We're going to get that cosine of theta minus pi, which means going in the direction of theta and then subtracting pi, so rotating around by pi in the negative direction, is going to point in exactly the same way. It's going to point in the direction of the green line. So cosine of theta minus pi is also going to be negative cosine of theta, and sine of theta minus pi is going to be negative sine of theta. So this gives us a few identities that we can work with, a few more identities that we can determine based on the unit circle. So we can see from the circle that if we add or subtract pi to the argument of a sine or cosine, we're going to get the negative of that back. On the other hand, what if we took tangent of theta plus pi? Tangent of theta plus pi is going to be sine of theta plus pi divided by cosine of theta plus pi. Sine of theta plus pi we just worked out is negative sine of theta. And cosine of theta plus pi is negative cosine of theta. But the negatives now cancel because we've got one on the top and one on the bottom. And so we get that this is just sine of theta over cosine of theta, which is tangent of theta. So we get that tangent doesn't change when you add pi to the argument here. So tangent of theta plus pi is equal to tangent of theta. And you can use these facts to work out what happens with the other other three trigonometric functions when you add or subtract pi. This is something that we can run into sometimes. Let's look at what happens if we add something else. What if we take a particular angle, let's put something in quadrant 2 this time, and we call this angle theta. And we have some point, I'm now going to label it x0, y0, because as the x and y coordinates corresponding to theta. And now I want to ask, well, what is sine of theta plus 2 pi? we can use the same sort of argument or construction that we did before, where to get a sine of theta plus 2 pi, we go ahead and rotate by theta the way that we've done, and then we continue rotating around by another 2 pi. Now 2 pi is a complete circle, which means that adding 2 pi means that we're going to go completely around the circle and in fact wind up with a coterminal angle. You'll remember that when we take an angle and we add 2 pi radians to it, we get an angle that's coterminal with the original one. But sine and cosine and the other functions of an angle only depend on the terminal side of it. And so since theta plus 2 pi is coterminal with theta, this means that sine of theta plus 2 pi is going to be sine of theta. And similarly, cosine of theta plus 2 pi is going to be equal to cosine of theta, and so forth and so on. And of course, we could add another 2 pi to it, or another 2 pi to it, or subtract a bunch of 2 pi's, and we know that we would continue to get a bunch of angles that are coterminal with the original one. So we have the following fact, which can be very useful. For any integer k and number theta, sine of theta plus 2 pi k is equal to sine of theta cosine of theta plus 2 pi k equals cosine of theta. And of course, because this is true for sine and cosine, it's also true for their reciprocals. So secant of theta plus 2 pi k equals secant of theta, and cosecant of theta plus 2 pi k equals cosecant of theta. Now, of course, the same thing is true also for tangent, because tangent is built out of sine and cosine. So if sine and cosine take the same values, then tangent's going to take the same value as well. But in fact, we can do something better than that with tangent. And the reason for that is the following. Let's recall what tangent is, how we compute tangent here. Tangent of theta is equal to y0 over x0, the way that I have this written out. However, y0 over x0 is also a way of talking about the rise over the run of this blue line. Because if I move from the point x0, y0 down to the origin, or rather the other way around, if I move from the origin to the point x0, y0, I will have risen by y0 and I will have run by x0. In this case, x0 is negative, indicating that we're moving in the left-hand direction. And the point is that tangent of an angle is the slope of the line containing the terminal side. So this is a great way to think about tangent in terms of some geometry, or rather the Cartesian algebra that we're used to with x coordinates and y coordinates and such. We have that cosine gives the x coordinate, sine gives the y coordinate, and tangent gives the slope of the line through that point. Now, in particular, what that means is that if I travel around by another pi, and I get a line going in the opposite direction, like we did last time, like we considered on the last page, the slope of the red line is the same as the slope of the blue line, because they are, in fact, all lying on the same line. So the slope is the same as the blue the blue line. And so in particular, this means that tangent of theta plus pi is equal to tangent of theta, not 2 pi. And in fact, we can do this over and over again. If we take an angle, theta, and we go halfway around the circle, we're pointing in the exact opposite direction, which means that we're contained in a line with the same slope and therefore the same tangent value. Similarly, the cotangent, which is just the reciprocal of the slope of the line, goes this way, goes up by pi's. So tangent of theta plus pi k equals tangent of theta for any integer k. Cotangent does the same thing. Now the term that we use for these types of functions is periodic. And these four are periodic with period 2 pi. What that means is that the values that these functions take keep repeating themselves over and over and over. If I know that sine of some angle is a half, then I know that if I keep adding 2 pi to that number over and over and over and over again, I'm going to keep getting those values. I'm going to keep getting 1/2. We'll see how this plays out in a moment when we start graphing these functions. Tangent and cotangent, on the other hand, are called periodic with period pi because they repeat when you just add pi to the angle inside rather than 2 pi. All right, so these are some very important facts that we have about the trigonometric functions that we can determine based on the unit circle. There's one more type of transformation that we want to talk about and see what happens when we change the input to one of these trig functions. And that's what happens when we make a negative. So I want to say, what is sine of negative theta, and how does that compare to sine of theta, and similarly for cosine, etc. Let's again sketch out what happens. I'll take something in quadrant 1 again. Let's say I have this angle theta, and I've got the point x0, y0. And now I want to consider what happens if I look at the angle negative theta. Now negative theta is going to rotate around the circle by the same amount, but it's going to go in the counterclockwise, in the clockwise direction. It's going to go in the opposite direction to our normal ones. And so we get this point down here. Well, how does the red point correspond to the blue point? You'll notice that we've got quite a bit of symmetry here, that what's going on the upper half of the graph is reflected in what goes on the lower half of the graph. So the picture that we have on top, the blue picture and the red picture, are exactly mirrored of each other. And what that means is that this point down here at the bottom is going to be x0, negative y0, because when we move from the blue point to the corresponding mirrored red point, the x values stay the same, the y values go to their exact negatives. And that is going to be encoded in what happens with the sine and cosine. We have that sine of negative theta will be equal to this negative y0, but y0 was sine of the original theta. So we see that when we take sine of negative theta, we get negative sine of theta out of it. But let's look at what happens with cosine. Cosine of negative theta is equal to the x coordinate that corresponds to negative theta, but that's just x0, which was exactly cosine of theta to begin with. So we have these two facts for how sine and cosine deal with plugging a negative, the opposite of an angle, into them. And we can use that to determine what happens with the other trig functions as well. So we get that sine of negative theta is equal to negative sine of theta. By the way, this is what we call an odd function. This is the fact that characterizes being an odd function, where if you plug the negative a negative input into it, you get the negative of the input of that input. Then cosine of theta, negative theta rather, is equal to cosine of theta. And this is what we say is characterized by an even function. Now, tangent of negative theta is going to be sine of negative theta over cosine of negative theta, and when you work all that out, you get to negative tangent of theta. So tangent is another odd function. Secant of theta is the reciprocal of cosine, and cosine of negative theta is just cosine of theta. So secant of negative theta is just secant of theta. Cosecant of negative theta is going to be negative cosecant of theta, and that's because cosecant is the reciprocal of sine. And then cotangent of negative theta is negative cotangent of theta, because cotangent is the reciprocal of tangent. So these facts are very helpful when we go to computing the sine and cosine and tangent of various complicated functions and try to prove various identities involving taking negatives of the inputs to these functions. Let's now start looking at what the graphs of these functions are. We want to understand what the graph of sine and cosine and tangent, etc., are when we start plotting their values on a normal graph. So we're going to be sort of moving back and forth between what happens on the level of the unit circle and what happens in the graph of the trigonometric functions as functions. All right, so let's graph y equals sine x. Now, it can occasionally get a little bit confusing here because now we're using x as our input to sine. Normally we interpret that as an angle, so the x that we have here is different from the x that we use on the unit circle. I'll do my best to keep that from getting too confusing. So let's graph y equals sine x. Now we are going to use the unit circle in order to help us out here. Pardon me. I just want to make this a little bit more convenient to work with. And what we're going to do is we're going to graph sine by graphing various special points. So we're going to make ourselves a table, and we'll have x and then sine of x over here, which will be our y values. Now there are certain special values of x that we want to deal with. We definitely want 0, pi over 2, pi, 3 pi over 2, and 2 pi. We want all the multiples of pi over 2 that we get when we do one full movement around the circle. So let's look at what we have here. So when x is 0, that means that we're plugging an angle of 0 into sine. Well, that corresponds to an angle that just points towards the positive x-axis. And that point has coordinates of 1, 0. So in particular, this means that sine of 0 is 0 because sine corresponds to the y-coordinate here. Well, then we move on to pi over 2. If we move over here to pi over 2, then we're looking at the angle that goes straight up, and we looked at this just a minute ago. That goes through the point 0, 1 on the unit circle. Sine of pi over 2 is going to be the y-coordinate of that point, which is 1. Then for sine of pi, we're going to go around to an angle of pi. That gives us a coordinate of -1, 0. And so sine of pi is 0. We'll go to 3 pi over 2, which is an angle right there. That points straight down, giving us a point of 0, -1. And so we have that sine of 3 pi over 2 is -1. Finally, we're going to have an angle of 2 pi, and 2 pi goes all the way around the circle and comes back to a line that's coterminal with our original one, heading straight off to the right, and so sine of 2 pi is 0. So here we've got a few points, and let's mark them out here. Now, when you're graphing these functions, sine and cosine and so forth, these are the points that you're going to want to use. At the very least, you want to use the multiples of pi over 2, and they're the ones that you want to note on your graph. So we'll look at pi over 2, pi, 3 pi over 2, and 2 pi. Notice that the y values of our points here, the sine goes between -1 at the minimum and 1 at the maximum. And this corresponds to the fact that the maximum y value of a point on the unit circle is 1, and the minimum y value is -1. So in fact, sine of any number is always between -1 and 1. So let's sketch this out. So we know that when x is 0, sine is 0. When x is pi over 2, sine is 1. When x is pi, sine is 0. When x is 3 pi over 2, sine is -1. And when x is 2 pi, sine is 0 again. So here are a few points on the graph of sine, and in fact the curve that contains sine goes through these all very regularly and smoothly. So that's what part of the graph of sine looks like. But what about further to the left. What about negative values? We know we can plug negative values in. We know we can plug any values we like in. Well, the great thing about working with sine and cosine, as I mentioned before, is that they are periodic, which means that if you want to know what's happening to a value of sine at one point, you can just look ahead or behind by 2 pi to see what it did there. So for instance, when I want to know what's sine of negative pi over 2, right here, what I can do is I can look 2 pi further ahead over here to 3 pi over 2. And I know that whatever sine does on the right-hand side of this 2 pi long bridge is what sine's going to do on the left-hand side as well, because sine behaves exactly the same when you move by 2 pi along the graph. So, since sine of 3 pi over 2 is -1, sine of negative pi over 2 is also -1. Now this corresponds to, over on the unit circle, what happens if you go to an angle of negative pi over 2. That means that you're moving counterclockwise, a quarter of a circle, which means that you're getting an angle which is coterminal with the angle we had before, 3 pi over 2, pointing straight down. And we can continue going. So if I want to know what happens at negative pi, I look forward to see, well, what happened at 2 pi more than that? What happened at pi? And we see that sine of pi is 0, so sine of negative pi is also 0. And then negative 3 pi over 2, when I plug that into sine, that's going to be the same as if I plugged in pi over 2 into sine, and that gives me 1, because that's 2 pi removed. And finally, if I want to know what happens at negative 2 pi, well, I can just figure out what happens at 0. And I know that sine of 0 is 0, so I can plug in this point here. So you'll see that if I just want to graph out a basic graph of sine, I can mark my x-axis with intervals of pi over 2, and then my graph starts at 0 at the origin and then goes up and then down and then down and then up and then up and then down and then down, so forth and so on. So we'll finish up the graph by going down, up, maxing out here at negative 3 pi over 2, coming back down. And of course the graph doesn't stop at either of these points. It's going to continue going and doing its thing forever. So the graph of sine gives us this wavy line that goes on and on and on with a period of 2 pi forever. And so that's what a graph of sine of x looks like. And really, you can see why this is happening by thinking about what happens to the y value on the unit circle as you increase the angle that goes in, as you increase theta. When we start with a theta value of 0, with an angle of 0, we have a sine value of 0 because we've got a 0y coordinate. But then, as we start moving, we're going to move up and get higher and higher y values, and then eventually start coming back down, getting lower, bottoming out here at -1, continuing on, going up, and looping around and around and around. And that's exactly what's going on here with the graph of sine. All right, so that's how we graph sine of x. Let's graph cosine of x, which is actually going to be very similar. It's going to follow a very similar pattern. It's going to look very much the same. It's just going to start in a different place. So let's do that here. We don't even need to make a table for this. So I'm going to be working on cosine in red. So cosine of 0 will be given by the x-coordinate of the point 1, 0, which is 1. Cosine of pi over 2 is given by the point 0, 1 on the unit circle, which gives us pi over 2. Cosine of pi corresponds to the point -1, 0, which gives us a cosine of -1. And a cosine of 3 pi over 2 is 0, because that's the x-coordinate of that point. And then a cosine of 2 pi is the same as the cosine of 1, so we get 0.1 up here. So you'll see that we followed the same sort of pattern as sine, just basically shifted by a certain amount. And we can do the same sort of pattern over here on the left, where we go down until we hit -1, back up until we hit 1, and then go back down and fill things in here. So when you're graphing sine and cosine, you follow the same sort of pattern. You're going to want to note the multiples of pi over 2. Pi over 2, pi, 3 pi over 2, 2 pi, and the negatives as well. And you're going to want to keep going up and down and up and down and up and down. And the only question is where you start on the graph when x is 0, when your input is 0, and which direction you go. So sine, the graph of sine starts at 0 here, and then goes up to the right. So we go up, then down, then up, etc., and continues that pattern off to the left. Cosine starts at 1. Cosine of 0 is equal to 1, so it starts at 1 and then falls down on either side and moves along like that, like the graph shows. So this is what the basic graphs of sine and cosine look like. Let's consider what happens with tangent, because tangent is a little bit more complicated, a little bit more interesting. And that has to do with the fact that it's not defined everywhere. So now, let's graph y equals tangent x. We're going to want to start doing the same sort of thing. We're going to want to make note of the points pi over 2, -pi over 2, out to pi, and then to -pi. But because tangent has a period of pi rather than 2 pi, we don't need to move any further than this in order to get a good sense for what the graph looks like. Now, to understand what's going on here, the best thing to do is going to be to think about tangent in terms of the slopes of the lines being defined by the various angles, as I mentioned before. That really is the best way to think about tangent. So let's start off with an angle of 0. We have that tangent of 0 radians is 0. Notice that the blue line is horizontal, which has a slope of 0. So we have the point 0, 0 on the graph of tangent. Now let's look at what happens as we start moving further up. If you look back at some of the work that we've done already, we can see that tangent of pi over 4 equals 1. So that corresponds to this angle right here, an angle of pi over 4, or 45 degrees. So So tangent of pi over 4 is 1. So in fact, we can sketch in pi over 4 here, 1. But then what happens as we start getting bigger? What happens as we start taking angles that are getting closer and closer to pi over 2? Well, what you'll notice is that the slopes of these lines keep getting larger and larger and larger. They keep getting steeper and steeper and steeper. So we could say that as x goes to pi over 2 from the left, so this notation means that as x gets closer and closer to pi over 2 from below, so we're taking numbers smaller than pi over 2, but we're moving closer to them, tangent of x gets larger and larger. So the slopes of these blue lines keep getting bigger and bigger and bigger and bigger and bigger, and then tangent isn't even defined at pi over 2. What this actually is an asymptote, and I'm going to use yellow to indicate my asymptote here. And so what happens is that the values of tangent keep getting bigger and bigger as the inputs to tangent keep getting closer and closer to pi over 2, and we get a pattern that looks like this. So we get that the values of tangent are just heading off, getting arbitrarily large. Okay, well, that's what's happening on one side. What about the other side? Well, on the negative side of things, you'll notice that a very similar sort of phenomenon happens. As we move further and further negative, as we approach negative pi over 2, tangent of x gets larger and larger, but in the negative direction. So as x approaches negative pi over 2, this time from the right, tangent of x gets larger and larger in the negative direction. And so what this means is that we have another asymptote over here at negative pi over 2. And so, in fact, we are going to have values of tangent that look something like this. So what we get is that tangent is sort of squeezed in here between a couple of asymptotes, at least this part of it. This isn't the complete graph of tangent yet. But what we see is that tangent goes all the way up, all the way down. Unlike sine and cosine, tangent doesn't have a maximum or a minimum. Tangent can be as large as you like, can be as small as you like. And it's just going to keep going up and up asymptotically here. Now, what we do know is that tangent is periodic with period pi. What that means is that if you take the graph of tangent and shift it by pi on the plane, you're going to get a copy of it. It's going to lie exactly on itself. So we have that tangent is periodic with period pi, which means if we shift this whole thing over by to the right by pi, we're going to get something that looks exactly the same. So we're going to be getting something going down like this, something going up like this, and in fact, we're even going to be getting an asymptote over here. And this asymptote is going to be at x equals 3 pi over 2, because that's pi to the right of the asymptote at pi over 2. And similarly, when we move to the left, we're going to get another copy of tangent, going down like this, and we're going to get another asymptote, this one, at negative 3 pi over 2. So this is what the graph of tangent looks like, and it keeps repeating itself over and over again, all the way to the right, all the way to the left, forever. And so this is what the graph of tangent looks like. All right, so really quickly, we're going to look at how we construct the graphs of secant and cosecant, and those are built off of the graphs of sine and cosine because of the reciprocal identity. So let's look at the graphs of y equals cosecant x and y equals secant x. So let's start with cosecant. So the way that we're going to do this is we're going to start with a graph of sine. So we're going to start with a graph of sine, and so we're going to put in our standard points, pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And we want to label the important points of 1 and negative 1 on the y-axis. And we know that the graph of sine starts at 0, goes up, and it goes up to 1, comes down to pi, goes down to negative 1 at 3 pi over 2, and comes up to 2 pi. Similarly, on the left, it comes down to pi over 2, comes up to pi, comes up to 3 pi over 2, and then down to 2 pi. So this is what the graph of sine looks like, and cosecant is 1 over sine. So let's see what we can say about cosecant related to sine. So first of all, notice that if sine is equal to 1, then cosecant will also be equal to 1. So for instance, we have that cosecant of pi over 2 is equal to 1 over sine pi over 2, and sine pi over 2 is 1. So we have that cosecant of pi over 2 is equal to 1. Similarly, cosecant of 3 pi over 2 is negative 1, because it's 1 over negative 1, what sine is, and so forth and so on. So we have that cosecant matches up with sine at the peaks and the valleys of the graph of sine. Other than that, though, they don't match up, because as sine gets smaller, cosecant gets bigger. So if sine is getting smaller than 1, cosecant is getting bigger than 1. So what we get is that, for instance, at this valley here, at this peak, rather, of sine, that's going to be a valley of cosecant. And similarly, the graph of cosecant is going to come up and match the graph of sine at all of its peaks and valleys. Also note that the graph of cosecant, it has an asymptote. Where sine equals 0. So remember that cosecant is 1 over sine of x. If sine of x is 0, then cosecant's undefined. And in particular, if sine of x is very, very small, if sine of x is very close to 0, then cosecant will be 1 divided by a very, very small number, which is in fact a very large number. So what we get are asymptotes, we get an asymptote at 0, at pi, at 2 pi, anywhere that sine is equal to 0. Negative pi, 2 pi. And so to finish up the graph of cosecant, what we do is we indicate that these pieces of cosecant each go off towards infinity or negative infinity as appropriate as they approach their various asymptotes. So the graph of cosecant makes these valleys coming down from infinity above and these peaks coming up from infinity below, and matching with the graph of sine. So in this sketch, the red is the graph of cosecant x, and we build it out of the graph of sine x, which is in the blue. And once we've seen this, graphing out secant is almost exactly the same. We're just going to start with the graph of cosine rather than sine. So if we want y equals secant x, then we'll do something very similar. We're going to have our pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, and we've got our special values of 1 and negative 1. The graph of cosine starts at 1 and then comes down to pi over to 0 at pi over 2, then to, sorry about that, that was really off, then to negative 1 at pi, and up to 0 at 3 pi over 2, and over here at 2 pi, and then down the other way, like this. And so if we want to graph out secant, first of all, it's going to match up with cosine whenever cosine is 1 or negative 1, and then we're going to get a bunch of asymptotes again. We're going to get asymptotes wherever cosine is equal to 0. So in fact, we're going to get asymptotes at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and further down the line. And then the graph of secant is going to look like this. So here's how we work out the graph of y equals secant x. And that's how we can graph out the 6 trigonometric functions. We're going to do a lot more with these. We're going to do transformations and see how we can use the graphs of these trigonometric functions to represent a lot of very important things in real life, a lot of real life applications.